Welcome to this new video of Module 2, IPv4 Address Exhaustion, Coexistence and Transition. In this module, we'll be talking about tunnel-based IPv6 transition mechanisms. We'll discuss the following topics: Introduction to tunneling, 6-in-4 tunnels, tunnel broker, 6-to-4, 6RD, and DS Lite. Tunnel-based mechanisms are used to send packets with one IP version over a network that doesn't support this version of the protocol. To do so, the packet to be transmitted is encapsulated in an IP packet of the version supported by the network that must be traversed. As we'll see, tunnels may be static or automatic. Static tunnels have their endpoints configured in a static, usually manual manner. Automatic tunnels establish all or part of their configuration automatically and do not require explicit configuration. Tunnels may also be point-to-point or multi-point. Point-to-point tunnels connect only 2 points on a network, 2 tunnel interfaces, such that packets that enter one end of the tunnel are encapsulated in another IP packet that traverses a network to reach to the other end of the tunnel, where the original packet is de-encapsulated and delivered. Multi-point tunnels connect several network points or tunnel interfaces. A packet that enters the tunnel is encapsulated and can be delivered at one of several possible tunnel endpoints. Tunnel-based mechanisms are the most common transition mechanisms. Many tunneling mechanisms have been defined. Many have become obsolete, and still others are currently being developed. IPv6 can be encapsulated directly in IPv4. Otherwise, a GRE header can be used or UDP to encapsulate IPv6 in IPv4 to traverse NATs. IPv4 can be encapsulated in IPv6. We'll now see further details of some of the most popular tunnel-based mechanisms. Tunneling 6-in-1. 6-in-1 tunnels encapsulate IPv6 identified with protocol number 41 in an IPv4. These are static, manually configured point-to-point tunnels. IPv6 can be encapsulated directly in IPv4 or a GRE header can be used. As the image shows, to traverse an IPv4 only network, one end of the tunnel can be configured on one router and the other end on another router connected to the IPv6 internet. Thus, IPv6 connectivity can be provided through the tunnel to the entire network connected to the router establishing the tunnel. The tunnel can also be configured from a host, which therefore obtains individual connectivity. Tunnel broker. Tunnel brokers are agents that provide automation for the creation of 6-in-1 tunnels as a service. A user usually signs up for tunnel creation on a web page, and the tunnel broker will configure its tunnel endpoint in the tunnel server. The tunnel server is normally a router connected to IPv6 internet. Depending on the user's operating system, the tunnel broker will also provide instructions for configuring the user's endpoint of the tunnel. Once both endpoints are configured, the operation of the tunnel is similar to that of 6-in-4. These are just some of the free services that implement tunnel brokers, all of them using different protocols for setting up the point-to-point link. 6-to-4. 6-to-4 tunnels encapsulate IPv6 and IPv4. They are automatic and multi-point, and they use a prefix reserved exclusively for this transition mechanism, 2002:16. They also require a public IPv4 address. The 64 prefix is constructed by appending the /16 prefix we've already seen and the 32 bits of the IPv4 address so that a /48 prefix is obtained. The 6-to-4 router creates a virtual 6-to interface that de-encapsulates IPv6 packets in IPv4. The 6-to-4 relay is a 6-to-4 router that also connects the IPv4 internet to the IPv6 internet. Two forms of communication are possible: between two 6-to-4 hosts or between a 6-to-4 host and a native IPv6 host. 6-to-4 tunnels are important for two reasons. Firstly, because they are widely available since they are automatically enabled on Windows operating systems when they have a public IPv4 address. Secondly, and more importantly, because they have evolved into 6RD, which is a very useful and widespread transition mechanism used by different ISPs. 6RD shares many of the features of 6-to-4. It encapsulates IPv6 and IPv4. It is also an automatic and multi-point tunneling mechanism. But because it is an evolution of 6-to-4, it also incorporates many improvements. Firstly, it doesn't need a reserved prefix since it uses the ISP's global unique addresses. In addition, it can use private IPv4 addresses, provided they are unique within the environment where the 6RD mechanism is used. Also, it continues to use an IPv6 prefix plus an IPv4 address, forming what is known as a user's 6RD prefix. This is a very good solution for ISPs, as 6RD is transparent to the rest of the Internet. It is only used within the ISP, where it controls all of the elements of this solution. Just as is the case of 6-to-4, two forms of communication are possible: between one 6RD node and another, between a 6RD node and a native IPv6 node. All major equipment manufacturers support this mechanism. In practice, many ISPs have already deployed it. Now, let's try to understand how 6RD addressing works. The 6RD delegated prefix is a prefix that the end user's CPE can use to provide IPv6 addresses to the internal networks. It is made up of the 6RD prefix that the ISP uses for this transition mechanism and an IPv4 address or part of an IP address. In some cases, part of the IPv4 address can be eliminated when it is the same for all of the nodes in the network. If the 6RD delegated prefix is shorter than 64 bits, the CPE may create 64-bit subnets. Let's see an example. The 6RD prefix used by the ISP will be a /32. Therefore, in this case, N is 32 bits. 2001:DB8. The IPv4 addresses used by all CPEs and internally by the ISP are part of the 10.0.0.0/8 prefix. 8 bits will be shared by the entire network, so only the 24 bits to the right will be used. Thus, the 6RD delegated prefix will become a /56, comprising the 32 bits of the 6RD prefix plus the 24 bits of the IPv4 address. Let's say that the CPE's IPv4 address is 10.0.0.2. We would take the 24 bits to the right, 0.0.2, convert them to hexadecimal notation, and append them to the 2001:DB8 prefix to obtain the /56 prefix we see here. The numbers in red represent the IPv4 address embedded in the IPv6 address. This means we would have an 8-bit subnet ID to create up to 256 possible /64 networks. Let's take a look at how two 6RD hosts communicate with each other. We have a 6RD router with an IPv4 address 10.0.2.2. We convert this address to a hexadecimal notation and append it to the IPv6 prefix used by the ISP 2001:DB8/32. So, we obtain a /64 prefix we can use to address hosts on a LAN served by this 6RD router. Here we can see that host A would have an IPv6 addressing ending in 2. Likewise, with any other 6RD router within the scope of the ISP with an address, for example, 10.0.6.6, we would follow the same process to create a /64 prefix, which we would use to address host B, which would have an address ending in 6. From then on, these two hosts are ready to communicate among themselves. How? Native IPv6 packets would travel over the LAN to the 6RD router, where they will be encapsulated in IPv4 and sent to the other 6RD router. There, the packets will be de-encapsulated and sent to the IPv6 host, host B. The IP addresses involved in the process are the source IPv6 address, host A address, and the destination address, that of host B. Here, the trick, highlighted in red, is that when the host sees the destination address, it knows that it is using the 6RD process. So it will look for the embedded IPv4 address of the destination router, in this case 10.0.6.6, and this will allow packets to reach the correct router. When a 6RD host must communicate with a host of the IPv6 internet, we need an element known as a 6RD relay to connect both worlds. The relay announces to the internal network a known anycast address, which will be used to send 6RD traffic. To the IPv6 network, the relay will announce the prefix used for the 6RD service within the ISP. Thus, host A will send IPv6 packets through the 6RD router, where they will be encapsulated and sent over IPv4 only infrastructure to the relay, where they will be de-encapsulated and sent to host B as native IPv6. Here too, IPv6 traffic is sent to the 6RD router as native IPv6, where it is encapsulated in IPv4. The source address is that of host A. The destination address is a global address of host B. When the 6RD router notices that the destination address does not belong to the prefix used for 6RD, it will encapsulate in IPv4, always using its source IPv4 address and the known anycast address for this 6RD service in the ISP's network as destination address, 192.88.99.1. In other words, whenever a packet is sent to an address that is not part of the 6RD prefix, it will reach one of the relays implemented by the ISP. Once it reaches the relay, it will be de-encapsulated and sent over native IPv6. DS-Lite. DS-Lite is an advanced tunnel-based mechanism as it assumes a main IPv6 only network and offers IPv4 connectivity by encapsulated IPv4 in IPv6. It has been designed to help delay IPv4 address exhaustion by using a powerful NAT, where users share public IPv4 addresses. Here, the trick is that NAT is performed only once, in the central NAT, and not in each user's CPE. DS-Lite elements are known as AFTRs, Address Family Transition Routers, CGN, Carrier Grade NAT, or LSN, Large Scale NAT, for the powerful NAT, and B4, Basic Bridging Broadband, for the client creating the tunnel. Native IPv6 traffic is forwarded directly to the IPv6 internet. IPv4 traffic arriving at the CPE is encapsulated in IPv6 packets and sent to the AFTR, where the packets are de-encapsulated and NATed before being sent to the IPv4 internet. Now, let's see how DS-Lite works. IPv6 traffic travels natively from beginning to end. Instead, IPv4 traffic will be sent to the CPE, or the B4 in this example, with 10.0.0.2 as its source address and a global internet address 1.2.3.4 as destination address, such that when it reaches the B4, it will be encapsulated in an IPv6 packet with the source address of the B4 IPv6 and the destination address of the AFTR IPv6. The packet will traverse the main network, which is IPv6 only. When it reaches the AFTR device, the IPv4 packet will be de-encapsulated and NATed. What happens is that the source address, IPv4, is changed to one of the AFTR's public addresses. In our example, 1.1.1.1 will be used as the source address and 1.2.3.4 as the initial destination address for the packet. So an answer can reach the AFTR device, which will perform the NAT. Thank you for your attention. We have just discussed tunnel-based mechanisms. In our next video, we will talk about mechanisms using translation.